Okay, so I'm going to go over an example of the last question from section 6.1. Turns out that's a really good question, and good from a practice standpoint, because it practices quite a bit of trigonometry. It's difficult for that reason, just because there's a lot to know. The problem in and of itself is the steps are simple, but there's a lot to know. So worth going over. I'm going to try to get it done in 15 minutes, because that is the time constraint I have with the program that I'm using. Otherwise, I've got to do a part 2, and I'd rather not. So to save time, I actually already put this into Y1 and Y2, and I've already parameterized the window. I'm going to show you what I used here. I used actually, I believe this was negative pi over 15 and then positive pi over 15. I just made the denominator a little smaller so that I could see a larger negative value and positive value, a little more to the left and to the right of the parameter that they gave us here, or at least the interval that we're working on. I considered the fact that the range of this is going to be negative 2 to 2, right? You're talking about sine, whose range is negative 1 to 1. It's getting doubled. So we're not really going to need to see that much beyond negative 1, or sorry, in this case, negative 2 to 2. The range of tangent is all reals. So I just made the y min negative 5 to 5, and that was, I'm going to leave this up here in the video for at least a while so that you can see the window I used. So it's ideally, you should be able to put that into window. If you struggle with finding the right parameters for a viewing window, then you might want to do the algebra up front. Now, the trick with this problem is that you can miss some intersection points pretty easily. So having this graph can actually help you, right? Because I'm looking at this graph and I can see clearly, oh, there's 1, 2, 3 intersection points. We don't care about what's going on up here and over here, because we're fully in window. It's this region here. Right? We've got this interval contained within the window we're looking at. So looking at it, there's 3 intersection points. And let's see if we can find them with some algebra. We'll set these two things equal. Unless there's like an obvious identity. It's a good place to start with something like this is to write your tangent functions as a quotient of sine and cosine. I wouldn't bother substituting 9x with anything. I mean, you could in theory, but I think it's best to just leave it as 9x. Personally. Okay, and then if we divide both sides by sine 9x in this equation, it's going to cancel out the sine 9x, right, on the right side. So dividing both sides by that sine of 9x should give us 1 over cosine 9x equals 2. Now you could write this as a secant statement if you'd like. Secant 9x equals 2. I personally just thought it was more relatable to stick with the cosine function. We'll say cosine of 9x equals a half. And now we need to figure out, okay, well, what argument does the cosine statement here need? What does 9x need to equal in order to get cosine of a half? You could use like an inverse trig function here if you'd like, if you know how to work with those. I think it's easiest to just, remember, I'm going to cite these triangles quite a bit because I'm a fan of the triangles. I don't use the unit circles. I mean, essentially it's the same thing, but I like the special triangles over the unit circle. So I know that I'm dealing with 1 and 2. That's suitable for this pi over 3, pi over 6 unit circle. Remember, opposite of pi over 3 is root 3. Opposite of pi over 6 is 1. And then here we have a 2. And remember, cosine puts the adjacent, or the x value, over the hypotenuse, or the r, right? A adjacent over hypotenuse, or again, x over r. If you see this as the radius using the unit circle. Anyways, the cosine of pi over 3 is what gives us a half. So that means that 9x must be equal to pi over 3, right? In which case x itself is pi over 27. Now, this is something you could miss, potentially, if you don't already have the graph ready to go. However, there is another value, another reference angle that gives us a positive 1/2 out of cosine, right? Cosine is also positive in the 4th quadrant. So it should be true that 9x can also equal, right, think about staying in the positive quadrant, then we're going to rotate root 3 counterclockwise. We can also rotate pi over 3 in the other direction, counterclockwise, and for to put us in the 4th quadrant where cosine is positive. So this should also be true, right? 9x could also be equal to negative pi over 3, which means x can actually be plus and minus. There's the minus. Pi over 27. Right, and it turns out the values they gave us here actually end up being the intersection points. But here algebraically determine that they actually are the true intersection points and not just the window they want to work over. Okay, so let's see. I'm just going to shrink this up. So at least we got the intersection points taken care of. Now, if you notice, there's a third intersection point. That one, in some ways, maybe is even easier to miss if you don't have the graph, right? And it turns out that's probably the one you're most likely going to miss if you don't have the graph. So one thing to consider is maybe you're familiar enough with the sine and tangent function to know they both start at 0. Like if their argument is 0, their output's going to be 0, right? They're both odd functions. That's something to consider here in a second. But here maybe if you, after writing tangent as a quotient, right? Well, I know that this is going to be equal 0 wherever its argument is 0, and they both have the same numerator now, right? If sine 9x is 0, assuming cosines won't be 0, but cosine at 0 is 1, so we're okay there. If 9x is 0, we're going to get a 0 on both sides here and both sides here. So we also need to consider that x equals 0 as an intersection point. Of course, 9x equals 0, then x equals 0. So we've got 3 intersection points to work with. Now, if you consider the fact that sine and tangent are both odd functions, right? Well, odd functions are symmetrical about the line y equals x, right? And that's good for us because that means that this is symmetrical. We don't need to necessarily go across the whole negative root 27, or sorry, negative pi over 27 to positive pi over 27. Let me delete this real quick. Okay. We can actually just go from here, the center, to this edge, and then double, and use some symmetry to hopefully maybe make the calculation a little easier. So let's double, and we'll pick up at this intersection point of 0, and then we know this to be the positive root 27, right? We're not going to work with the negative root 27, which is that point over here. All right, so along this interval here, from 0 to pi over 27, the red function, that's the one that's turning back down, right? That's the sine function. We know it's the sine. We can always check in y equals, but it turns back down, right? So it's got to be sine. This is the one that turns up. So that's the tangent function. So the function that's on top then is the 2 sine 9x. 2 sine 9x. And the function below is the tangent function, tangent 9x dx. All right, so this is what we have to integrate. Now, I'm thinking I might not make it to 15 minutes based on what we have, because there actually is still something I want to work out with this tangent. So I'm actually going to stop the video here in case maybe this is all you needed was to get this set up. I'm going to proceed with the remainder of this problem, namely how to get this integrated without much trouble in part 2. So I'll stop here and we'll call this part 1.